the matrix inverse, because as we go on, we're going to use this to derive basically an auxiliary field model for the Ising Hamiltonian. And if I use Einstein's summation rules, remember when I have, say, Aij minus 1, that's the inverse matrix elements. The elements of the inverse matrix, not the inverse of the elements themselves. So what we're doing is we're going to use this on the Ising model with spin variables that I was calling sigma. So Hubbard-Stratonovich transformation. Of the Ising model. The reason we're doing this is to incorporate fluctuations into our treatment of the order parameter. So for the Ising model, the object that's transformed by the Hubbard-Stratonovich transformation is this, which goes in the partition function. So the partition function is just a trace over all spin variables, right? And so these are my plus or minus 1. And so those, the sigma I, sigma j, okay, are analogous to, well, I've written things in terms of a vector, B here, and a matrix. So the JIJs will be like the inverse of A. Before I derived this in sort of vector notation, last time I wrote the Hubbard-Stratonovich transformation with fields. I think the fields were phi and gamma. So with Einstein's summation, it might look more familiar, but bottom line is all we need is this. Okay, so now my determinant, instead of A, of the inverse of J. Okay, so I've moved this over to the, say, left-hand side. Now this integral is over fields that have been introduced, or, vectors that have been introduced, x. So instead of calling those x, I'm going to call them phi, so it looks more like a field theory. Now I have an integral now. Of n of these fields. Okay, and what's inside the integrand? Is the analogy to that top line. So now it's the inverse matrix. And here's where your sigma ends up. Okay, so like I said, you have a decoupling of, this is like an interaction here. This is what's hard to take the trace of. But once you do the Hubbard-Stratonovich transformation, you'll have one of these fields decoupled, or one of these spins decoupled, sorry, but at the cost of an auxiliary field, phi. And you have to do this integral over, infinite dimensional integral over phi. So it's not, maybe it's not even clear right off the bat that this is somehow easier. But there's things we can calculate from the auxiliary representation that we can't by doing the trace directly. So let me start doing a few manipulations on this. Let me change the field variables. By just scaling out t. And then I'll write the full partition function. which remember has that trace. 1 over 2t. And so I have enough room, let me write it. So I have a constant out front that has all those determinant and the 2 pi's. Let's see, I need the integral. Okay. And let me just say, I gotta add this, I can write another exponential. And let's see. Right, and J, you know what J is? It's that n by n matrix with all the elements Jij. Okay, so that's the inverse matrix that you have to worry about up here. And generally that C, this constant, if you want to call it that, you know, because it falls outside, like out front of the trace, and you know, it just doesn't affect thermodynamic properties. So unless otherwise, we're just going to drop this. Okay, so what else do we have to know? 1 over 2t, right? Yeah, okay. So another interpretation of this is, you know, we've eliminated interactions, if you will. Phi I. And this is just sort of the philosophy behind, you know, field theory in some sense, that you have this fluctuating, sometimes we call it a molecular field or a mean field that fluctuates both, again, with temperature and with spatial position. We'll see more explicitly how this relates to the order parameter. But the idea in the field theory is that, you know, it's somehow the averaged, you know, the time and space averaged, or at least the time averaged if it has a spatial dependence. Order parameter, which is in some sense the expectation value of the spins. But we'll come back to that. So the main advantage again of this is that we can take this trace, which is written over sigmas, right, and move it into here. And here we have a decoupling of I and j. So we just have to take that simple trace for that second term in the exponential. And the trace is, the sum over all those spin variables is exactly the same as how I calculated it in mean field theory. So look back at your notes. Remember I explicitly wrote out what this notation means. It's a product of all the sums of sigma I equals all possible states of the individual sigma I, which is just plus and minus. Okay, so I'm going to get sick of writing this. So let me introduce a shorthand notation. I'll call big D phi. And that turns this into a functional integral, they call it. So then my partition function is just a functional integral. Let's see. Let me keep the trace outside for a minute. Okay, so I'm just rewriting the same thing. So it's minus 1 over 2 pi, sum over ij. I. Okay, so now when I move that trace inside, I'm just dealing with this term here. So functional integral. Okay, so remember last time you basically have a plus and a minus. So you get an exponential with a minus argument and a plus. So that gives you your hyperbolic cosine. And I've just written this in the exponential. So I've taken a log of it. So then it's a sum over all fields I log 2 cosh. So I can also write this as just the functional integral over e to the minus s and call s an action, just a functional. Oh, I ran out of space. Okay, so I've done the trace, and now what's left is calculating this, infinite dimensional functional integral over the remaining fields phi. So depending on the form of that action, S, you can either directly do that integral analytically or not, essentially, right? So So in this case, what we're going to do first is look at the simplest approximation to doing this integral. Okay. Approximation. Okay, that approximation is called the stationary phase of the saddle point method. And what it involves is just replacing that functional integral over, so big integral over all fields of that exponential with just the maximum value, of the integrand. Okay. So you're basically just going to get rid of the integral and approximate it with the exponential of s evaluated at the mean value of the field, say. Okay. So that's z, functional integral. So the approximation is just the replacing of that entire integral with e to the minus s. And you have to evaluate this. I'll call it phi bar, where again, remember this is a multidimensional field vector, has n components. So it has to minimize the action because you have e to the minus s. So it's the maximum term that occurs in the integral. Okay, there's nothing saying that this is a good approximation. Okay, but it's just the simplest one you can do. So to obtain this, all you need to do is find a minimum of the action, if you want to call it that, of that functional s. Okay, so you're just going to take a derivative of it with respect to the field phi I. Okay, so I have it written right there. Okay, so the derivative of s the first derivative of the action at that value that you want to find at its minimum is 0. That defines a minimum. Okay, so I just have to look at my s up there. I should get and log 2 cosh x. Again, the derivative is a hyperbolic tangent. You've seen that before. Okay, so I just have this, which looks familiar. In order to pull out, say, phi I or phi j bar, I need to just matrix multiply by j. Okay, so that'll give me something like this. Tan hyperbolic tangent. J, ij. I need a j in here then. Okay. If you have translational invariance, then things simplify. The site index shouldn't matter. Then you can just write this as phi I is equal to phi. And then you can just define this thing as j, Do you recognize that? It's just the mean field equation. So all this tells you is that by taking this approximation here, the saddle point approximation, that you recover a mean field theory. Okay? So this is just a way, way more complicated way of getting exactly the same thing we already had. Okay, so that tells you another interpretation of mean field theory. We're going to look at this functional integral in much more detail for the general case of the Ising model. Okay, and basically what I want to do with this is calculate the two-point correlation function, which I mentioned before. That allows us to derive the exponents for the two-point correlation function and also define the correlation length and calculate its exponent. And before I do that, I just want to do one more interpretation of mean field theory. Okay, so the first time we saw mean field theory, it was a theory where we threw away fluctuations. Remember, we threw away sigma I. Can't remember what we called it. Sigma j. We set those to 0. That gave us a mean field Hamiltonian. So that approximation is the same as doing the saddle point approximation in the functional integral. Okay. And as I want to show you real quickly, it's also the same as looking at an Ising model with your Jij's being of infinite range. Okay, so the final interpretation of mean field theory is that it has to do with an infinite range Ising model. So this is sort of an aside. But I think it's an important interpretation again. Okay, so we're going to come back to this functional integral. Well, actually, let's use it here. So if I can, we'll just do the Hubbard-Sirtanovich transformation here in the case where we have an infinite range Ising model. So it doesn't matter where your I and j are. Doesn't matter if they're nearest neighbor or if they're, a mile apart. Let's just define jij is some constant j over n between those two spins. And then any sum we have, sum over jij, will just be j.
The meeting has ended because it had only one participant for the last 30 minutes.
Guess Will's not coming. So we can write our Hamiltonian then, just using this vast simplification. Let's see, do I need the field here? I'm going to say no. So I have two independent sums, 1 over I, 1 over j. Sigma I, sigma j. So right away you see that if you have that situation and you can write it, then you can write it as just the square of these two sums. That should tell you that I should be able to solve this exactly. Because what I claim is that it's the trace, over the interacting piece that's hard. So just writing things like this, the interpretation is that, I have this infinite range interaction. Okay, so it's good practice for the Gaussian integration. So the only thing we need is one field in the Hubbard-Sirtanovich. Okay, some constant. So it's not a functional integral in this case. So that lets us write our partition function. Okay, so let's write that. So I have a trace, one field, and let's see. Oh yeah, sum over the variables. Right. So again, I can pull in that trace and just perform it over that sum. I'm missing a square. I feel like I am. Okay, so I have, let's see, this is two sums here, right? I just erased the Hubbard-Stratonovich transformation. What do you guys think? Is that right or not? All right, so in the one variable case, okay, we'll go with it. Let's just check this. So you should get, once you take that trace, will be a sum again, log, yeah, it's going to be 2 cosh phi over t. Okay, we'll go with that. Double check everything here. That sum just gives you a factor of n. This is what happens here. You get an n in front and an n here. So your integral can also be written as d phi e to the minus, call it s. So this is the action appropriate only for the infinite range model, say. Where s is all this stuff here. Okay, so we've seen something like this many times. You know, phi squared and phi. So the value of this field that minimizes that action again is just obtained by taking the derivative. So you can see how the mean field equations are basically going to come out here. Oh, minimizes the action S. Okay, and so one important thing that we can see from this is we can relate this functional S, or in this case, this function S, to a free energy. There's a simple expression for the free energy. So let's take the derivative. You know, and then we can relate this free energy to the, you know, we're seeing the mean field equation here. So we should be able to recover the mean field free energy. Okay, so let's expand the full function in a Taylor series around this minimum. Okay, so the first term is just S at phi bar. The first derivative is 0 at the minimum, right? That defines the minimum. So the next term in this Taylor expansion will be the second derivative. And I'll have to evaluate that like I did this. So phi equals phi bar times phi minus phi bar. Okay, so I've just defined which way do I want it? Phi minus phi bar, like that. We know this thing's positive too, by the way, since I'm looking at a minimum. But regardless, we can write the partition function. I kind of want to pull that n out. Just pulling this out. Let me just write that n in farm. Oh, did I get the sign of the action wrong? Is that what you're saying? Yeah, this term should be plus and minus. Yeah.
And also delta phi is squared.
Yep. Sorry. Okay, so I can feed in that approximation. Let's just do it up to second order. I'll write it down here. So I get a constant term. So now I have an integral over the field. It's equivalent to an integral over this very varied field, if you want to call it that. It's variational field. So it's going to be d delta second derivative phi bar delta phi squared. There, that's just a Gaussian. So this can be solved with Gaussian integration. It's just a general fact of life that the only time you can solve these problems exactly is when you have a Gaussian somewhere. You just manipulate everything to find that Gaussian integral and do it. Otherwise, you're basically hooped. Okay, so if we solve that, then the partition function looks something like this. Sorry, this is small. You know what it is, phi bar. I pulled that n out because I want to be able to take a limit when n goes to infinity. So when I take the thermodynamic limit, I should be able to, get an exact expression. So let's just look at the free energy. So the free energy is T log Z. So I'll have two terms. Okay. Let me get the minus signs wrong. No, Tn. Then I'll have S evaluated at phi bar. I'm going to say minus here. Okay. I don't know if this is right. Whatever. I have a linear term in n and a term that's logarithmic in n. So the linear term should dominate, right? So when I take that limit into infinity, I can get an exact expression. So minus t n s. Good. So I should compare this to the free energy from the original mean field theory. Which we wrote a couple days ago. And if I wrote the action correctly, then they should be equal. Where's my S? Okay, so you have to identify M, big M, from our expression from a few days ago with phi bar. NT log looks good. Gosh. Right, so these two are equal. So this is another way of looking at mean field theory. It's the same as saying this here, that your Ising model has infinite range interactions. And there's no difference between spins that are local on the lattice and ones that aren't. So you're actually losing this idea of the dimensionality in everything. So it's very, very simple. Sort of mathematically, it's pretty much unphysical. And it's equivalent to mean field theory. Say infinite. It's probably enough interpretations of mean field theory. You have any questions about this?
So last class you said the result of mean field theory for dimensionality greater than 4 is exact.
Right. So we'll see that.
Then you said it's not physical.
Well, infinite range, I would say, maybe isn't physical. But 4D, well, that's debatable, whether 4 dimensions is physical. I would say yes. But again, the range of interactions is somehow mapped to dimensions. So imagine you have 1 dimensions, and you have something like interactions between I and j drawn by those lines. I mean, you could also build up a 2-dimensional, object by further connecting these things. That might be something like a ladder. If you keep going in different patterns, you can build up higher dimensions. Interactions define dimensions in some sense. So this is like an infinite, maybe dimensional model. But so what we haven't seen yet is this connection to 4 dimensions. So 4 dimensions is the critical dimension where mean field ceases to become exact, and then we have to worry about these exact solutions. So 1D is sort of special. 2D and 3D are, I'd say, the interesting cases. So I want to get back to calculating the spin-spin correlation function. Somehow this takes me several classes. Maybe there's an easier way to do it, but. So let's forget the infinite range and just go back to the general Ising model. Okay. Put my field back in. No, I want to do it right. So I'm going to do something with a magnetic field. I'm going to generalize a magnetic field so that it's site dependent. And this is more a mathematical device than a physical, realistic physical situation. But we're going to use that quite a bit. So again, the field is in some sense just the lowest order object that you can couple to, say, the 1 point or the order parameter in some sense. So you could define other fields. I mean, in some sense, Jij, you could say, is just an interaction strength for 2 spins, just like the interaction strength for 1 spin. You could generalize these models in many ways. But Bi is for our purposes, a mathematical device. Okay, so I haven't defined this yet. What is a spin-spin correlation function? I'm going to call it G, apparently. Gij, because it tells you something about the strength of correlations between 2 different lattice sites, say, or 2 different spatial positions. And there's 2 equivalent ways of writing this. The first is like the fluctuation term. Okay, so it's like the fluctuations of the variable sigma on site I multiplied by the fluctuations on site J. And the fluctuations are occurring, around the background magnetization. This is completely mathematically equivalent to this expression. Oh, I forgot a bracket here. Right, so these mean thermodynamic average, or, trace, 1 over Z, sum of all states. The expectation value, I guess is what you call it. So when you have the expectation value, so if you just multiply this out, you have sigma I, sigma J, right? And then you have terms that are summed. And the expectation value of an expectation value is an expectation value. So that gives you this. It's called the connected 2-point function, right? It's like the spin fluctuations above somehow the mean order parameter. Okay, so that's a definition of the object. I think I'm going to use this here in the calculations. And so as the first step in exploring how this object looks for the Ising model, I just want to do a proof. That for the specific Ising model, the Gij that I can write this as a second derivative of a free energy, or the free energy, where each derivative or partial derivatives taken with respect to the fields, respectively at site I and j. And I'm going to set the field equal to 0. So this is really only valid for the Ising model with none of these fields. And then we're going to use this to calculate this thing here. Okay, so we have to prove that thing first. And remember what we're working towards, because it'll become lost, the point will become lost soon, is those, remember I wrote that expression for the 2-point correlation function, Gij, you know, that defines the correlation length. And so we want the critical exponents. We want a definition of the correlation length from this, right? So that's the length at which I and j are somehow related, or the states of spin variables in I and j are related. And from that expression, we define that length, and then that length diverges at the critical point. And that divergence is governed by a universal exponent. But it also tells you that the length scale, or the concept of a length scale, disappears. And again, that's the important concept in pretty much this whole class, okay? Okay, so let's start with this proof. Okay, so let me start with the free energy. Take the second derivative. Okay, let's act with one of these derivatives and hold one back. I probably told some of you guys this before. Once I was teaching second year, and one of the students asked me why my 2's didn't cancel. Just remember, these are my partial derivatives. Okay, I've held back on j. But what am I doing? Oh yeah, I've taken the derivative of the log. That's where the 1 over z came from here, right? So now I have two terms. I have to take this derivative, you know, using chain rule or whatever. So I'll write it like this, minus t. And I'll have two partial derivatives, right, of z, as I should, dj. Okay, so now let's put in the Ising model. I'll put it in the full Hamiltonian. And I'll write down an expression for the partition function, has the trace and everything in it. There's my trace. That's the thing that we need the partial derivative of with respect to one of those on-site fields. Okay. And the whole effect of that, the whole reason we take these derivatives, they're like a generating function for the derivative in the sense that it brings down the sigma I in this case. Right, and if I set the field to 0, then all I have left is e to the 1 over 2t, and then the interacting piece. So that's a general device, the introduction of these fields to give yourself a generating function for these partial derivatives. Because then this looks like an expectation value, right? If I normalize it by the partition function. So you already see the elements that are going into this. It's that, I'm taking, it's like I have a generating function, I'm taking partial derivatives. Those partial derivatives bring down, in this case, an individual field. And then I need to write this, I need to normalize this in order to get one of these pieces out, one of these expectation values. Okay, so therefore, properly normalized. That's sigma I. This is just the definition of Z, basically. And that whole thing is just the definition of sigma I, because there it is. Okay, I could take another derivative up at this stage here. Oh, no, sorry. Before I set the field to 0, I could pick another site, J, take the derivative, pull down another sigma. So I would see that then the second derivative with all fields equal 0 has a t squared. Right. So again, all I need to do is normalize that thing, maybe get rid of that t squared. And I'll have this piece here. Okay. T squared Z. So this thing should give me sigma I, sigma J. Right. That's it. That's the proof is basically just understanding how these generating functions work. All my t's work out, so I should have minus t, second derivative of the free energy. Okay, proofy enough for me. Okay, so let's use that expression to calculate the functional integral. Okay, so remember, after we do the Hubbard-Sturgeonovich transformation, we have this big functional integral. Forget that infinite range thing. I'm going back to the original functional integral, where I had e to the minus s. And I've performed the Hubbard-Sturgeonovich transformation on that precise Hamiltonian. Log 2. Sorry about this. Just leave the fields in. Maybe it's not the precise Hamiltonian. Maybe I didn't have the site-dependent field before. Yeah, see, I got my sum over I. Looks good. Okay, so that's my Z. I know how to define a free energy from that Z. That's the functional integral. And that's the expression I need to calculate. So let's use that. And I'll write in terms of, instead of Z, I want to use, instead of F, I want to use Z. So BI, BJ. So I think this is what I want. And you're going to multiply this one by this one. Okay. I'm going to do something confusing now, but it makes the calculation easier. So maybe it's actually less confusing. I'm going to change variables. I'm going to get rid of those fields. So I just basically want to get rid of this Jij that's going to cause a problem down the road. So this is kind of a note. So I'm just going to call this a fluctuating magnetization. And all it is the field, but it's like the field and all the J values that are affecting the field. You don't need a name for it, but I could also just write another phi. Just rescale phi, but let's just use M just to keep things separate where I've introduced this step. Magnetization. So it's going to be the sum over J's. Yeah, right. of the inverse by j. I could do matrix multiplication by j. And so every time I have a phi, I want to write it as a sum over j m's, basically in that action. So all I'm doing is basically, I'm not changing the first term, but I'm putting a sum into that hyperbolic cosine. These are equivalent. I think this one's easier. Although 2 pages down the road, I might change my mind, but I don't think so. So that just gives the action's equivalent. This is the same S. That's not the inverse matrix anymore because I have 2 fields, right? So the inverse cancels one, but the other remains. And here I need to have that matrix, Jij, like that. So again, I'm going to use this. It's equivalent to that thing. I can relate, let's see. I can write my Gij in terms of m's then. That's one way of thinking about it. Is it equivalent? Is it mi mj minus the expectation value of mi mj? Well, we should check that. So let me relate expectation values between fields, phi, and this fluctuating magnetization. So I can imagine writing, say, that action, or this action, either one of them. But I can imagine also redefining the fields so that, my phi I plus bi, say, is just some single field. And I've moved that magnetic field into the interaction term. That changes the way the generator interacts, or the derivatives of the generator behave, say. Okay, so let me just imagine that for a minute. So if I did that, bi, I suppose. So if I did a change like that, what I would get is just an action that looks a little different. So you can basically always change these. You can always do these types of transformations on the field variables. You just have to take care of the Jacobian. You gotta just not forget about the Jacobian in the functional integral. Otherwise, any of these change of variables essentially don't matter. So which one am I doing here? I've changed S. Let me just look at phi for a minute. Here's my single field now. So if I take derivatives with respect to B, Let's work with z, so I still have a functional integral. I won't worry about the Jacobian, because the bi's aren't variables. Oops, I forgot my d. So that's fine. But what I'm doing when I take this derivative now is I'm pulling out, so it's going to be 1 over 2t. Then it's going to be something like j minus 1, let's see, phi j. E to the minus, you know, it's an exponential, so it's the same action. I'll just write it like that. So all that is the magnetization M somehow, right? So the idea that this thing, where did I write it here? All right, so here's a derivative with respect to the same field. I get the expectation value of this. If I want to use that magnetization, all I gotta do is switch this variable, and I'll get the expectation value of the magnetization somehow. So to be precise, I think it'll be 1 over, it's 1 over z, right? Then I should write this as a functional integral over m. Again, no worries about the Jacobian. It's just mi. I've summed over j, so that's just mi over t. And then the action I could, again, is equivalent between phi and m. Is that right? 1 over t? Yeah, that's right. Mi. I just have t on the wrong side here. Okay, so the expectation values are the same. So I can write the Gij, the thing that's behind here, in terms of expectation values of either the fluctuating magnetization or the original sigma variables. And, you know, that's the difference. I won't do this one, but the second derivative, you could check it if you were so inclined. So I can write, instead of this, my Gij in terms of m squared and m. Okay, so let's do a calculation of this in these variables. Let's do our first calculation with the saddle point approximation. Which should be mean field theory. I'll just say in mean field theory. And that's when the partition function, which I'm now going to call a functional integral over m, is approximately equal to just the maximum value of the integrand, which I'll write like that. And M bar is the configuration that maximizes or minimizes S, right? Okay, so it's fairly straightforward now. So F, by definition, I have a partition function minus d log z. It's just t times. So if you're wondering what this action is, again, it's basically just the free energy. So the Landau free energy, remember the thing we derived for mean field theory? The action is just the slight generalization of that. And remember, mean field theory just means getting rid of the integration. That's why I can write it like that. And I'm going to write this as, let's see. I've changed the m variable, so I need a sum Jij. Okay. So let's calculate the partial derivatives with respect to those on-site fields, BI. Okay, so that's all we're doing here. So the first one, right, so let me do a minus. So this bad boy should equal T1 over Z. I'm just writing identities that we've already used. Partial with I. I think I erased it maybe. Okay, I can call this sigma I here. Right, that's what I just wrote behind the board. But if I take the partial of, well, I guess it's easiest to take it with F. So what I'm doing is this, if I take the partial derivative of that expression with respect to the field, then I need the field only occurs in this piece, B, and I'm taking again that derivative of log 2 hyperbolic cosine, which is just tan H. So Jij mi, I can leave this in. If I went and took the partial derivative of, if I found the minimum explicitly of that free energy, then I would get, I would see that this is just my field M, I. So this is the mean field. Again, I've just rederived the mean field theory equation for the order parameter, M. So check that if you're not sure. Okay, and so my Gij, the 2-point correlation function, is the second derivative. Okay, and I've taken one derivative out, which is this here. And I've just written that in terms of the partial derivative of that m, which is that tan h expression. Okay, so hyperbolic tangent. So I'm almost done. I'm going to need a self-consistent expression here. So let me actually take that derivative through. So that's the only annoying part. Let me write it like this. I use an index L here. And the derivative of the hyperbolic tangent is 1 minus tan h squared. This is chain rule. JIL ML plus B T. I don't know. I got to set B equal to 0 somewhere here. Okay, so just taking a derivative. Just to simplify things, let me call this object here. That's just your mean field magnetization squared. Right? Makes sense. That's what I basically wrote up there. So in the shorthand, I have a derivative of m with respect to b still, which I got to deal with. And that thing, really is just written right up there in terms of Gij. So I can write this whole thing. Let me think. I need a t out front. So 1 over t, so 1 over L, IL, G, so it's Lj at 0 field plus delta Ij 1 minus m squared. Okay, so that's a very general expression for Gij. It's kind of ugly, but whatever. Yeah, 1 over t, sum over L. Yeah, IL, so you have a sum over L, so it's GLJ there. You have that delta function, which just came from that derivative, right? If you're taking a derivative of a field I with respect to another field J, that's where that delta function came from. And then I've just written 1 minus, this whole thing is just shorthand that I called big M squared. So next class, what I'm going to do is calculate this Gij. So remember, I'm in the mean field approximation because I've done this here. Basically, I've done this. That gives me mean field. I have this expression now. I know what this m is. I'm going to do 2 calculations. One where I'm approaching the critical point from above, and so m is equal to 0. And then I get a nice expression because this piece all drops off. And all I really have to do is calculate this thing here by inverting these matrices. And then there's a much harder calculation for when I'm approaching the critical point from below. And then I can't assume that this magnetization, this mean field magnetization, is 0. And since it's so hard, that's what you're doing on your assignment too. Okay, so that's a 2-point correlation function. We need to solve it next time for m equals 0 in Fourier space. So I have to introduce a lattice Fourier transform. Okay, and that calculation will take most of the class. So just don't lose track of what we're doing. If I get through that, yeah, so by the end of next class, I'll have a definition of the correlation length, hopefully, right? At least in this case here. Okay, so see you guys on Wednesday, and your assignments are due in 1 week.